Hello everyone, thanks for checking out this particular video. This will be on project management and in particular the different techniques and processes that we use to be able to manage projects using linear programming as well as other techniques and strategies to help us to be able to streamline everything so that it works in a fashion that's most efficient and cost effective. And this video will serve as an aid for those people who are taking some sort of data-driven decision-making type course where you're using Microsoft Excel to be able to model situations, doing linear programming to help you in either managing a project or help you to be able to find cost-effective solutions to certain situations. So our learning objectives here will be, first of all, how to plan, monitor, and control projects using the PERT method or the CPM method. And the PERT method is called the Program Evaluation and Review Technique method, and CPM is Critical Path method. We also want to understand as well as determine what do we mean by the earliest start, earliest finish, latest start, latest finish, and slack times for each activity within a project. And so we want to look at those because depending upon how we actually start, how we finish, and each sub project within a particular project, or each activity, as we call it here, within a project, that will sort of define what our critical path would be for it. And from that, we can kind of get an idea of how we need to start, how we need to finish, and what wiggle room that we have. And of course, we're calling the slack time, that's going to be the formal phrase for the wiggle room that we have. We also want to understand the impact of variability in activity times on the project completion time. And in this case, what we'll be doing is using what we know about our situation, as well as if we've had similar situations, we're going to use or interject probability into it so that we can realistically get an idea of how much time we have from the I guess you would say the optimum time, or the time that we're hoping that we meet. Okay, so for instance, if we're wanting to get a project done in 10 weeks, realistically, based upon past experience and some of the challenges that we may have, uh, probability wise, that may range anywhere from, let's say, 9 weeks to 11 weeks, depending on what our situation is. And so when we interject a probability into it from past information, and plus with other challenges that we know is going on in that particular project, we may be able to give a more accurate estimate of what the completion time would be, or at least a range. And with that, assign a probability of completion based upon the time. And so that's what one of the things a probability helps us be able to do. We also want to develop resource loading charts to plan, monitor, and control the use of various resources during a project. Okay, so such things like if we want to use like a Gantt chart or things like that, we'll see some information about that. Objective number 5 is where we actually use the linear programming techniques in this. And so if you've been watching some of my other videos, you've noticed how we started from the beginning, just talking about basic linear programming techniques, and we've modeled various type situations using that, including assignment models, transportation models, transshipment models, networking models, min-max models, max-min models, pricing out strategy type models, all those things. And so now we're using linear programming to help us to be able to reduce the total project time within a particular project that we're working on. And by taking a lot of those things into account that we have to for projects, we can kind of see what's going to be our critical path and our most cost-effective path as well. And then finally, we're just going to touch a little bit on uh, Microsoft Project. We won't touch on this too much, but it's just to let you know that Microsoft Project is a way to be able to sort of organize all of this information. So when we talk about project management, it's a series of related tasks leading to a well-defined output. So in other words, basically we want to plan everything so that we can get the result that we desire. And so there's 3 phases to this. Of course, there's the planning phase, the scheduling phase, and the controlling phase. And of course, with the scheduling and controlling, there's sort of a cyclical type motion going on here, to where there's always going back and forth, and more so in between the scheduling and the controlling. But of course, based upon how things are actually going in our project, we may have to go back and do some additional planning on the fly if needed. But again, this part here, you try to lay out everything that you want, and then here you try to schedule it as best as you can, and then based upon when you're actually rolling out the project, you may have to adjust some things. So there may be some extra planning that may have to be involved, and some reshuffling of how the schedule goes to get all the activities within a project done. So what is project planning exactly? So we're asking stuff like, what is our main goal, our objective for the project? What are the various activities that constitute the project? In other words, what are the subtasks or the activities that we have to do in order to be able to say that if we get all these little things done, then the big thing of project X in this case will be accomplished. We want to know how are these activities linked, meaning what activities have to come first, what has to come second, what has to come third, what's going to be the last activity. Okay, we want to know what is the time required for each activity, and then what other resources are required for each activity. So for example, so let's say we were trying to build a house. And so to build a house, of course, we would first have to make sure that we have the land tilted so that we can put all the plumbing stints and stuff there. We'll also need to have the foundation done. Of course, the frame of the house will need to be made. Of course, the roof. And then once all that's done, then you would want to put all the drywall and sheetrock and all that in there. And so there's a process. You wouldn't want to build a roof before you lay your foundation. So that's why it's important for us to know what are all the activities that are involved and how are they linked, what comes first, what comes second, as well as what resources that we need. So once we're done with the first part, we will start to do the scheduling. So once planning is done, we'll actually start to schedule. So we have a good idea of how everything is, and we want to kind of lay everything out in linear fashion. So we want to know when will the entire project be completed, or probably a better way to put that is when do we hope that the project is completed? What is going to be the schedule for each activity? So in other words, now that we know how long it takes each activity, what's going to be the start and finish time for each activity? We want to be able to identify what are the critical activities of the project, meaning that what are the activities that if we don't get those done, then they create bottlenecks or they hold everything else up in the project. So we need to be able to identify that. We want to know what are the non-critical activities of a project. In doing that, we find where we may have some wiggle room, aka slack time, and we need to be able to identify where that is, because if we get into a crunch, if we have a situation on a particular project that we have some unforeseen issues, then we may have to do what's called project crashing, and we'll see that later on in the presentation as well. So we want to also know for each non-critical activity, by how much can we actually delay that particular activity without it affecting the original planned completion time of the project. And so again, that lets us know how much wiggle room we have, so that if we need to shift things around, we can. We also want to know what is the probability that a project will be completed by a specific deadline. And so as I had mentioned earlier, we know that if we plan for a project to be done in 10 weeks, that may not be realistic. And so it may be only a 50% chance we can actually get that done within that 10-week time. If we get a good range of when a project can be completed, meaning that what is the percentage that it can be completed early versus if it has to be completed late, what gives us a good probability of be completed within a certain time. Normally anywhere north of 90% would be a good barometer for that. And so we just want to get that information based off of what we're currently dealing with, mixed with if we have information on past projects that have been very similar and how long it's taken those particular projects to be completed, then we want to factor that into the mix. And so again, that's where our probability and statistics comes to play. So once we're done planning and we do our initial scheduling, then from there, what we want to do is control the project. And so in controlling the project, we want to monitor things like, are we on schedule, are we behind schedule, or we are ahead of schedule. We also want to see how much money we're spending, and we want to see, is that going to be equal to, less than, or greater than the budgeted amount. And so one way we can keep track of that is to see, I guess, sort of divide everything out and say if we're spending, let's say $100 million, and I'm just throwing out a number there, $100 million over 10 weeks, then that means it's basically going to be $1 million a week. And so we want to see, are we actually keeping on target with keeping our cost within $1 million, sorry, not $1 million, $10 million. So are we keeping our budget of $10 million each week as needed? And if not, then what could we do to cut cost in one area so that we kind of get back aligned to what the original budget was. So we also want to know, are there enough resources available to finish the project on time? We may have a situation where we have a lot of resources deployed in some activities, but not so much in the others. And if we have a situation where we're having some difficulty getting a particular activity done, we may need to pull resources from one area to another. And we need to make sure that if we're in a situation like that, we still have enough resources to be able to get the other non-critical activities done while putting some extra support on the critical activities so that everything gets done on time. And of course, the million-dollar question, which is, what is the best way to finish the project in a shorter amount of time and at the least cost? So this is pretty much the name of the game. Get it done fast, get it done as cost effective as possible. So now, of course, if we look at all the phases together, we see that we got the planning of the project. Of course, this is where all the meetings come from. Of course, the scheduling part is is more laying everything else out, and then controlling is just monitoring and kind of it's sort of like a feedback loop where you just um, look at everything and sort of revise and replan as needed. And of course, one of the ways that we can kind of see a bird's eye view of how everything is laid out is by using a Gantt chart. And so what this Gantt chart represents is a situation where we are trying to map out all the things that go on whenever an airplane, let's say, comes in, deplanes, and does all things that it needs to do to pick up a new set of passengers to fly on to another city. And so this could be considered to be an actual project within itself. And so, of course, we have several different activities that go within this project. So, of course, one activity is deplaning the passengers and doing the whole thing about baggage claim as far as getting the customers their bags. Of course, fueling is also involved. If we have any cargo or mail on that particular airplane, we need to get that off. We need to have drinking water available. Of course, the operating crew, they need to do their aircraft checks. We need to board the new passengers. So we have all these things going on. And so the main point that I want to illuminate here is you see that there are some projects that start roughly at the same time. Well, some activities that start roughly at the same time. So all these things are starting roughly at the same time. And so then after that, we see that this is starting second, and then this is starting third, that's starting fourth, and then so on and so forth. And of course, we have a lot of things running at the same time. And so part of our planning and scheduling phase is to figure this stuff out and to know, all right, exactly when do we need to start this, when do we need to stop it, so that everything just runs seamlessly. All right, so one of the ways that we sort of figure out how everything is laid out in a project, and what I mean by that is how our activities are ordered and how much time each activity is going to take, and you know if we're going to find any slack time. What it is we can lay out a particular project by doing a project network. Okay, and this is our way of using networking theory to be able to look at a project abstractly, but yet still have the information in it to be able to give us what we need to know so that we can identify what the critical path is in the project as well as what is our available slack time. And so when we use project networks, of course, it lets us know where our starting and ending points are. It inherently lets each of the activities be unique, and it also could let us know that, hey, we can have some activities that could possibly be just projects on their own. And so we need to be able to identify that as well. So for the activity times and resources, it also gives us clues as to the estimates for cost, of course, accuracy and expertise as far as being able to lay out those things so that we can know where to put them of most use in our project. Now, whenever we are trying to break down everything, of course, this is one way of doing it. So let's say we have a massive project, then of course there are going to be sub projects within that. So um, this whole indention system just kind of lets you know the level of everything. And so here we have, of course, the major project. These will be the major subtasks will be indented over, and then the subtasks for that, and then of course down at the low level would be the activity. So we would plan to get down to the lowest level here and then kind of work our way back as we're actually doing the projects. And so this is another way of doing it as well. And I know when I used to work in industry, I saw this a lot as far as the level ID numbers. So whenever you see this, of course, the more numbers after the decimal, the further into the minutia you're getting. And so in this example, they're just saying, well, what do they need to be able to do to be able to launch a new operating system? And of course, for this would be the Windows 8. Of course, we're well beyond that now, but if we were trying to do that, then of course, it would be important to develop the graphical user interfaces. And we also want to make sure that earlier versions of Windows can be compatible with it, because of course as you're upgrading you want all the old stuff to be able to integrate to the new stuff. And of course a part of that is anyone who's using XP or Vista or Windows 7, you want everything that's running on those systems to be able to also run on Windows 8. And then things like being able to import files using those particular operating systems is something that you want as well. And so again, this is just an example of how this would look whenever you would take a particular activity and break it down, or a project into its activities, and then break down those activities into subtasks. So the two techniques that are most common whenever you are planning projects and trying to put them together is the PERT method and the critical path method. The PERT method is called the Program Evaluation and Review Technique, and the CPM method is called the Critical Path method. And so the Program Evaluation and Review Technique is probably the one that we will use the most here. And this is the one that allows us to be able to interject in some probability into our project. And so in particular, the probabilistic time estimates will help us find probability of having a project done by a specific date. And it looks at it by doing 3 time estimates. And so, of course, we have optimistic time, a pessimistic time, and then the time that we originally planned on. Okay. Now, for the critical path method, it takes more of a deterministic approach, meaning that we kind of assume that we know everything up front. And so in doing that, we just use a single time estimate and say, all right, well, we kind of know how long this takes, and we already know we're going to have issues here. So at that point, we can just kind of plan for all that. And in an ideal world, you would probably start off, if you did a project, let's say for the first few times, by using the PERT method. But then let's say you're, 50th time doing a similar project for a different company, you may want to use the critical path method, because at that point, you've probably seen all that you're going to see. So you'll pretty much know everything. And so again, that really just depends upon your situation, but we will focus on the PERT method. Now, just to give you a little history back on the PERT method and the critical path method here. The PERT method actually comes from a time in, I think it was in 1958. There was a Special Projects Office in the U.S. Navy, and they developed this particular method to be able to plan and control this missile program called Polaris. And the project involved, of course, thousands of contractors, as you could probably imagine. And the government still uses this particular technique or method to be able to monitor a number of government contract schedules. Now, the CPM method came out slightly before that in 1957, was developed by company ran by, I think, J.E. Kelly of Remington Rand and M.R. Walker of DuPont. And so it was originally used to assist in the building and maintenance of chemical plants for DuPont. And so, of course, I guess for whatever reason, they probably knew most of what went into building chemical plants. So that's why they took more of a deterministic approach. Okay. So just give you some background as to where these actual methods come from for managing projects. All right, so let me move this over just a little bit. All right, so for the situation that we have here, just to give you a general background as to what this is going to look like, we have some company called General Foundry. And so what General Foundry needs to do is they need to install a really expensive, highly efficient air filtration system in their main smokestack. And they've been putting this off for a while because, of course, it's expensive and it's going to take away from productivity time. But the local EPA for this company has basically said, hey, if you don't have this up, in about 16 weeks or so, we're going to shut down operations until you get it done. And so with that, of course, the companies kind of has their back against the wall and they're like, hey, we need to go ahead and get this done. And so what you see here is the various activities that need to happen just from a bird's eye view to actually get this air filtration system installed and working in the main smokestack. And of course, we also see what has to come first, what has to come second. And in particularly, what we see here is what precedes a particular activity. So what we see here is that activities A and B, of course, they do not have any immediate predecessors, meaning there's nothing that comes before them. So we basically start with these two projects. And then from that, we see that A is a direct predecessor of activity C. So that means building the internal components has to come before the construct collection stack. Okay. And so, of course, A and B both have to be done before they start to pour concrete and install this frame. So, of course, you see how all this stuff kind of fits together here. Now, how we're going to break this out to be able to get everything to look more in an abstract sense so we can see what comes first, what comes second, and what's running at the same time is we're going to draw this into a project network. And so the two most popular approaches would be the AON method, which is the activity on node method, and the AOA method, which is activity on arc. And what we mean by that when we say the activity, all the information that we need to know, like what is going to be the start time, the finish time, whether it's the earliest start time and finish time, as well as late start time and finish time, and how long the activity actually should go for. All that stuff is going to be on the node when we do the AON method. And the AOA method, all that information is on the arc, or the actual lines that connect the nodes together. And so we will be taking the approach of the AON method, which is activity on node. And so how we start this off is we'll make a dummy node to say this is where we're going to start. And then, of course, the two activities that do not have any preceding activities before it, we'll actually put those first. And then, of course, after that, then, of course, we'll build on. And we know that both activity A and B have to be done to be able to do D. And of course, activity A had to be completed before we do C. And we know that because of what we saw here. So activity A had to be done before C, and then activity A and B had to be done before D. So we're basically taking this information here and we are essentially just laying it out in network form. So let's go back. And then, of course, after that, we build on the rest. And you'll see that if you go back to that slide that showed all the other projects and what preceded them, we'll see that this is the layout for how General Foundry is going to get this air filtration system in their main smokestack. Now, we also, in the scheduling phase, we figured out how long in general was it going to take for us to do each of these activities. And so you see that if we look at each activity on its own, it's going to take about a total of 25 weeks. Now that means if we are actually doing each activity on its own separately. But as you know, there's going to be some of these activities that are going to run concurrent. And of course, our goal is to get this within 16 weeks per the situation I described earlier. So some of these will have to run concurrently in order for that to happen. Now, in determining the schedule of what's going to run when and how, we need to calculate what's called the earliest start time, early finish time, latest start time, and the latest finish time. And so, of course, we need to know all this because, of course, some activities will be done simultaneously. And this will allow us to be able to also identify what our critical path is. In other words, the activities that must be done and they must be done on time in order to keep the project going. And if not, we're going to have bottleneck issues. So this is the anatomy of a node. And so let's say we know that this is activity A and it's going to last 2 weeks. And so in this space here, we will have what is the earliest start time. And of course, if this is in terms of weeks, we'll say that the earliest start time for project A is going to be 0 because it's starting out at the beginning. For the latest start time, if we have a little gap in time before this has to be done, we can put that there. The earliest finish time would go here, and of course, corresponding earliest, latest finish time would go here. And so when determining the earliest start time and earliest finish time, we do what's called a forward pass. Okay, and so we'll describe that here in a second. So for the forward pass, it says if an activity has only one single immediate predecessor, then its earliest start time is equal to the earliest finish time of the predecessor. Okay, so let's say I have an activity B here and I have an activity A here. Okay, so let me do a better picture of this so that we can get a more realistic idea of what's going on. So I'm going to draw this a little bit bigger. All right, so let's say this is activity A, activity B. So it says if an activity only has one single immediate predecessor, which is what we see here, its earliest start time, which is right here, is going to equal the earliest finish time of the predecessor. So let's say the earliest finish time of A, which precedes B, is going to be 3. So what that means is the earliest start time for B is going to be 3. So that's what this is saying. If an activity has multiple immediate predecessors, then its earliest start time is the maximum of all the earliest finish times. So let's say we had another project C here, and let's say this was 4. So the earliest finish time here of activity C is 4. And let's say this also maps to there. Then now, instead of this being 3, this would have to be 4 because it would have to be the maximum out of 3 and 4. Okay, and so that's why we call it the forward pass, because we're taking whatever the earliest finish times are from the all the preceding projects and taking the maximum one. And so from that, we could figure out what are going to be our earliest start times and finish times. So for instance, let's say that project A starts in week 1, and let's say this starts in week 2. Then of course, if both of these projects last 2 weeks, then of course 2 plus 2 is 4, 1 plus 2 is 3. So that's how we're getting the start and finish times. And of course from here, we could keep on going. If this project lasts 3 weeks, then that means the earliest finish time would be 7 in that case. So that's kind of what's going on there. And of course, here, just got through showing this, that the earliest finish time is just going to be the earliest starting time plus the activity time. So that's what I was talking about here. The earliest finish time is the same as the earliest start time plus the activity time. So the 1 plus 2 equals 3 here. Same here. Earliest start time is 4, activity time is 3, so 4 plus 3 is 7, which will be the earliest finish time. And so this is how everything would look if we were doing everything. Of course, our start, just a dummy node. Of course, the start only precedes A, so we have A here. Activity time is 2, so we see that the earliest finish time would be 2. Since A is the only predecessor of C, the earliest finish time here is the same as the earliest start time there. Add 2 to get the earliest finish time for C. And then of course for F, same thing. C is the only thing that precedes F, so the earliest finish time here is the same as the earliest start time there. And of course, moving on, 4 plus 3 is 7. We're here. Now, moving, let's say down this way, we know that start, earliest start time is here, plus activity time. It's going to give us 3. Since for project D, A and B precede that, we go with the maximum of the earliest finish times, which is 3. So that's what goes here. Of course, 3 plus the activity time of 4 gives us 7 for the earliest finish time. And if we move here, we also see that activity E is only preceded by C, so we get the same earliest finish time here is the same as the earliest start time there. Plus 4 gives us earliest finish time of 8. And so now again for activity G, we have to take the maximum out of the earliest finish times to be able to start define the earliest start times, which of course in this case is 8. And then from there, project G's activity time is 5 weeks, so we get 13. And now for H, when we conclude everything, again, it has to be the maximum of the earliest finish times, which in this case is just 13. And of course, we'll get that done plus 2, and we're done in 15 weeks. And so I think I had quoted 16 weeks before, but I think 15 is actually what we're looking for in this example. So that is how to do the forward pass. So what the backwards pass allows us to do is to be able to figure out the latest start times and the latest finish times. And of course, it's just like the forward pass, but everything is the opposite. So if an activity is an immediate predecessor for just a single activity, then its latest finish time is equal to the latest start time of the preceding activity. So of course I'll draw this again. We'll use project A and B again. And so we know that the earliest start time and earliest finish time were here. The latest start time is here and the latest finish time is there. So what we're saying here is that if an activity is an immediate predecessor for just a single activity, like what we see here, then the latest finish time equals the latest start time of the activity that followed it. So here, if we're talking about the latest start time is 4, and A is the only thing that precedes it, then that's going to be the same for there, for the latest finish time. So the latest finish time equals the latest start time of the activity that immediately follows that. If an activity is an immediate predecessor for more than one activity, so let's say an activity, this one is an immediate predecessor for more than just one activity. So now let's take that again. Then the latest finish time is the minimum of all the latest start times. Okay, so here let's say that this is activity C, and let's say this has a latest start time of 3 weeks. So now we do the minimum of 3 and 4. And so now this will change, and instead of that being 4 now this would be 3 for the latest finish time, because we have to take the minimum of these. And of course, that's why we call it the backward pass, because now we're looking in this direction. And just like I did before, let's say if this was 7, then that means this would be 3, meaning that if the activity time here was a 3, and we know that our latest finish time has to be 7, then 7 minus 3 is going to give us 4. And let's say this is 8, so that will make our activity time 5. So if we have 8 here, take away 5, that gives us 3. And so the point of this is that whenever we do the backwards pass, we're already going to know what our finish time is for the last project. And so we're working from the very last project back to the original project. And so we would be going from whatever this value is minus the activity time to get the latest start time. Okay. And that is what this particular slide is basically trying to communicate. So if we look at that, then of course, knowing that we have to end in 15 weeks here, we subtract 2, we get 13. And so now, if you notice, 13 precedes F, and is going to precede G. So here the latest finish time here has to equal to the the latest start time here has to equal the latest finish time there. And same deal here. The latest start time has to equal the same as the latest finish time. We subtract 5 from 13, we get 8. We subtract 3 from 13, we get 10. And so moving on to E now, we see that the latest start time here is going to be the same as the latest finish time there. And looking here, 8 minus 4, activity time is going to give me 4. And so now we're looking at 4 and 10 as the latest start times. And both of these projects both of these projects come after C. So of course we have to take the minimum of 4 and 10, which would just be 4. Okay. Moving back down to D, we see that the latest start time here is 8, and D is the only activity that precedes G, so that's why this has to be the same. 8 minus 4 activity time gives us 4. Okay. Moving back up to C, we see that 4 minus 2 is going to give us 2. And now we're in a situation where C and D are both projects that are preceded by A. So here we have to take the minimum of 2 and 4 for the latest start time here to figure out the latest finish time there, which is going to be 2. And then of course, moving from D back to B, B only precedes D. So the latest start time here has to equal the latest finish time. And then of course from this point here, we see that the start or the dummy node here precedes both A and B. So here 2 minus 2 is 0 and 4 minus 3 is 1. So we have to take the minimum of the latest start times, and the minimum is going to be 0. So that's how we get back here. And so this is how we use both the forward pass and the backwards pass to sort of plan out what the earliest start times, finish times, latest start time and finish time to be able to sort of organize our project. And so now that we've laid out everything in this project network, we can also see where our slack times and our critical path are. So the slack time is any free time for any activity, and it's the difference in between the latest start time and the earliest start time, or the difference in between the latest finish time and the earliest finish time. And so critical activities have no slack time, and the critical path is the longest path through the network, and of course we could have multiple critical paths depending on how we choose things. So if we laid everything out in table form, this is how it would look. And we see that activity A, activity C, activity E, and G and H have no slack time, so they're a part of the critical path. And if we looked at it this way, then we see that A, C, E, G, and H all have no slack time, so that would be our bottleneck activities. And here, if we revise our slack time to where, let's look back here. So you see how we start here, that has 0 for the latest start time, and for here that has 1. If we revised everything to now to where we have both activities A and B starting at the same time, then you see that our critical path now changes. Well, we should say we have multiple critical paths at that point. And so now with activities A and B starting at the same time, we also have this critical path as well.